بسم الله الرحمن الرحيم أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم اللهم اخرجني من الظلمات الوهم وأكرمني بنور الفهم اللهم افتح علينا أبواب رحمتك وأنشر علينا خزائن علومك برحمتك يا أرحم الراحمين. बहुत सारी ज़बरदस्त दुआएं हैं इल्म के हुसूल के लिए जो आजकल हम लोगों को याद नहीं, क्योंकि इल्म की कोई तलब बाकी नहीं रही है. आज का लेक्चर में दो पार्ट्स हैं. इन द फर्स्ट पार्ट आई विल एक्सप्लेन द बेसिक Bayesian theory and calculation in the simplest possible format. So basically you have two random events. One random event occurs, it has two possible outcomes, E1 and E2. So you can think of this actually as a situation where, according to a random outcome, the world will change. It will go on one track or it will go on the other track. Like the Battle of Waterloo. If Napoleon wins, then the world will fall under domination of France, and if England wins, then the world will fall under the domination of England. So there is a probability of these two events, and one of these two events will take place, and then the world will be different. So now there is a second random event which will take place after the first one has, and the second random event will have different probabilities according to which state of the world you are in. So if you talk about the conditional probability of the second event given the first, it's completely clear and well defined and easy to understand that depending on the outcome of the first event, the probability of the second event could be different. If the French win, then the probability of a person speaking French is going to be high, randomly chosen. If the English win, then the probability of a person speaking French will be low. So the conditional probability is different in the different states of the world. So that is fine. Now what the Bayesian calculation does is it reverses this. It says that what is the probability that Napoleon won at Waterloo, given that one person that we meet is speaking French. So this is actually the reverse conditional probability. So now the question is, okay, does this make sense? And this is why this whole thing is very controversial. That's why Bayesian is not, nobody's teaching it in Pakistan, and there's a lot of controversy about the topic, mainly because somehow if you think of the time sequence, then this doesn't make sense. That we're talking about taking an event which occurred later, and then we say, okay, conditional on the outcome of this event, what is the probability of the first event? But when the second event occurred, the first event had already happened, so there is no probability. Okay, so there is some difficulty in understanding, interpreting. There are various ways to do that, and we will discuss that. But the point is that there is a controversy involved here. All right, so first we start with some technical definitions. So B1 is called a Bernoulli trial if it has two possible outcomes, and we code these outcomes as 1 and 0. And in order to be able to talk about it, we use the term success for 1 and failure for 0. This is just in order to be able to talk about it in language. Instead of talking about ones and zeros, we talk about success and failure. It doesn't really have any meaning other than that. So now the probability of success is P, and the probability of failure is 1 minus P, and sometimes you use the notation Q. This is so standard that P and Q are commonly used in this context. Now, the one thing that is not emphasized in conventional treatments is the timing. Timing is all important, and timing is never mentioned in conventional treatments. So that's why it becomes very confusing and hard to understand. there is a world which is the pre-trial, which is also called pre-experimental, and then there is the post-experimental world. These two worlds are completely different. Probability exists in the pre-experimental world when the trial has not taken place, and anything can happen. After the trial has taken place, then one of the two things has come true, and now there is no probability. Probability is finished. So now at that point this is called the post-experimental world. And these two worlds are very different, and basically all of statistics and also all of probability is about matching the post-experimental world and the pre-experimental world. In probability theory, what we do is we say, I know what the pre-experimental world looks like, so tell me what the post-experimental world looks like. In statistics, we do the opposite problem. We look at the post-experimental world and we ask, what is the pre-experimental world look like? So that's basically the two subjects. Alright, so now what we're going to do is to look at a sequence of two Bernoulli trials. So the first trial takes place and there are two possible outcomes. One of them is success and one of them is failure. So the probability is P1 and Q1. And so you have these two branches. The first branch shows the B1 equals 1 and the second branch shows B1 equals 0. After that we have the second trial. The second trial can also have its success and failure. So there are a total of 4 branches, success and success, success followed by failure, failure followed by success, and failure followed by failure. So now some basic probability calculations are that you see, basically probability is the same as percentage. So, for example, after the first trial, suppose that there's a 25% success probability and 75%. So there are 25 cases on the success side and 75 cases on the failure side. Then you go down further and suppose at the second trial probability of the B2 success and failure is 50% and 50%. Then of those 25, 12.5 will come in the first circle and 12.5 will come in the other circle. So basically the probability is calculated by multiplying. You take 50% and multiply it by the 25%. It's half of whatever was available to you in that circle. Now on the other branch, the probabilities can be different because we have a different case has happened. So now suppose that in the other branch, after B1 is 0, then B2 can be, the success probability is 75%. So then the failure probability was 75%, and then the success probability of B2 is 75, so the total probability will 0.75 times 0.75, and that will be the probability of success followed by failure followed by success, sorry. And then two failures will be 75 by 20 times 25. So it's very simple. It's very easy. There are two rules of probability. One is the multiplicative rule, and it says that if you want to calculate, I think I have it written down here. Yes, if you want to calculate the probability of E and F, two events, you can do it by multiplying. First find out the probability of F independently. That's called the marginal probability, very important term in Bayesian calculations. And then there is the conditional probability of E given F. So first you find out when E happens, because you want to find out the probability of both of the things together. So if one of them doesn't occur, then there's no chance. So you have to have probability of both of them separately. So take either one. This is the interesting thing about the Bayesian. You can take either one event to condition on. So we condition on F, for example. So we say, okay, what's the probability of F? We calculate that. Then we say, okay, given that F has happened, what is the probability of E given F? And we calculate that, and then we multiply the two, and you have the joint probability. So this is a very important problem. It says the joint probability of two events is equal to the conditional probability of E given F times the marginal probability of F. So there are three different probabilities: the joint, the conditional, and the marginal. So in the case that we were just discussing, if any one of the 4 circles at the bottom, these are the 4 possible outcomes, you can calculate the probability by this method. For example, the B1 equals 1, first success, and then second failure is equal to the probability first of success, B1 equals 1, times the probability of second failure followed, given that the first trial was successful. So this is just fine. This is a legitimate formula. B2 happens after B1, so the conditioning is proper. Now, the thing is that the other formula also makes perfect mathematical sense, and there is no difficulty in writing the mathematics of it. So you can say that, okay, instead of conditioning on B1, which is the one that happened first, I can condition B2. So we can say that, okay, it's probability B2 equals 0 times the probability that B1 equals 1, given that B2 equals 0. In some sense, this is an illegitimate formula because you cannot condition B1 on B2 because B1 happens before B2 happens before B1. B1 happens before B2. But mathematics doesn't know the difference, so you can do it. So let me show you. So from this formula, we can calculate the conditional probability, the reverse conditional probability. So I'll show it in a more dramatic example. So we have this situation where the Battle of Waterloo takes place. The probability of a French win or Napoleon wins is 1/4. The other was Duke of Wellington on the English side. He was commanding the British forces. So let's suppose that his probability of winning is 3/4. He actually won. It's not clear that these probabilities are right, but some people say it was very close. But anyway, this is just for the sake of calculation. So suppose that one of these victories happens, then 100 years later we are living in this world, and we randomly take a person who is living in the planet and we ask him to speak French. So does he speak French or not? So the thing is that if the Napoleon won, then likely the French would have established an empire and a lot of people would have been speaking French. And in the event of loss, this would not be true. So I'm making up these probabilities here. Suppose that randomly chosen person speaks French. The probability is yes, after a Napoleon victory, is 40%. And the probability that doesn't speak French is 60%. Even, if you have global domination, 40% is a pretty big number. So, on the other hand, if the French lose, then you have, so NF and then N no F, and then you have, if the French lose, then the probability of French speaker is only 10%, and the probability of not a French speaker is 90%. So this is fairly simple, straightforward setup. Now, so we have 4 events, NF, N and no French, W, Wellington and French, and Wellington and no French. And now we can calculate all of the 4 probabilities. The first probability is 0.4, 40% times 25%, which comes out to 10%. The second probability is 60% times 25%, which is 15%. And then on the other side of the branch, we have 75% times 10%, it's 0.75, which is 7.5%. And on the other side, we have 90% times 75, which is 67.5%. So basically, both sides, on one side you have 25%, it's split up into 10% and 15%. On the other side, you have 75%, and that's split up into 67.5 and 7.5. And this is the way it always is. All of the branches below must sum to the branch above. Okay, so now probability of that somebody is speaking French, given that Napoleon won or Napoleon lost, it makes perfect sense. It's the logical sequence. But probability that Napoleon won, given that the person I have is speaking French, doesn't make a lot of sense, because now if I'm living in this world where I'm looking at people, one of these two events, I'm living only in one of those two worlds. I'm not living in both of those worlds. I'm living in a world where Napoleon has won, or I'm living in a world where Napoleon has lost. So what happened on the other branch, I have no idea. It's not there. So to ask, and probably so basically we can make the calculation. Let's first make the calculation, then look at the philosophy. So what's the probability of The joint probability that n equals 1, f equals 1, we just calculated, it's 10%. What's the marginal probability of a French speaker? Now this is one of the keys. Now how do you get the marginal probability? Well, you have to look at all possible cases where you have the French speaker. So part of the marginal probability is the 10% on the French win side, but the other part is the 7.5% on the other side. This is the total probability of French speaking. If we look at the pre-experimental situation, suppose we are living in the world before the Battle of Waterloo, and we ask what is the probability that 100 years from now a randomly chosen person will be speaking French, then this is the correct calculation, because you have to sum up both of the branches. You have to go through the possibility of French win, in which case you will get 10%, and the probability of English win, in which you get 7.5%. Add them up and you get the 17.5%. Now, so I have the joint probability is 10% and the marginal probability is 17.5. So I can now calculate the conditional probability from this formula. It's 10% divided by 17.5%, which is 57%. So I have this is the Bayes formula. This is the famous Bayes formula. And why it became famous and why did it generate so much controversy? Because of the interpretation. Otherwise, mathematics, there is nothing controversial about the mathematics. It's straightforward. But the interpretation is very difficult, because now the way that you can interpret it, and this is why subjective probability is involved here. That suppose that I don't know which world I am living in. I don't know whether Napoleon won or Wellington won. And now I want to find out. So I look at a person and I say that, okay, I know all of these parameters and probabilities. So I say, okay, if a person is speaking French, if a randomly chosen person is speaking French, then the chances are 57% that Napoleon would have won. And so this is only a question of my knowledge. It is not a question about the real world, because the real world, one of the two things has already happened. So that's why the Bayesian calculation makes sense only in the subjective context. It doesn't make sense in the objective context, because in objective context, there's no probability anymore. So we are calculating a probability for something for which there is no probability anymore. And this is the case for all Bayesian calculations. They always do something like that. And so therefore, it's always about my knowledge about something rather than the reality of something. All right, that's the end of part 1 of this lecture. and next time we will discuss more about these Bernoulli binomial trials. No accuracy, zero. It's just fraud. Really, this is fraud. I mean, but because when you choose any kind of a non-random sample, you can do fraud, and by choosing the people that will be favoring, and it is done all the time. The toothpaste companies advertise that 9 out of 10 dentists surveyed recommend our toothpaste. Now, who did the survey? We chose the 10 people who we are paying salaries to. So, obviously, 9 out of 10 of them voted for us. They didn't say anything about how the survey was random. So, as long as the survey is not random, you can get any result you like.
So, ये जो data PPHS में है, उसके बारे में क्या?
Oh, when the our Federal Bureau of Statistics does sampling, they do their best to try to create a random a probability sample, not a simple random sample, and so they have some controls, and those are much more reliable.